In this chapter, we're going to be going through lipids and self-assembly. So this is probably my favorite chapter and unit of all, just because it's what I focused on for most of my research. So my research specifically had to do with lipid-protein interactions, so I focused a lot on lipid monolayers and lipid bilayers. So for this chapter specifically, I'll only go through lipid membranes and different ways of modeling bilayers so that you can kind of get to know what we can do with these lipids. So first I am going to go through a recap. So this particular section is just all about the recap of DNA structure and models and modeling the DNA histone complex. It's a very good overview just so that we have some of the knowledge from before and we're bringing that knowledge to lipid membranes, which some of it is useful, especially being able to model something as a spring or being able to know how something bends. So you'll see very similar approaches to lipid membranes as well. And once we get to lipid membranes and lipids, first we're going to go through an overview of lipids. Next, just a quick overview of what lipid self-assembly is, why they even self-assemble, different preferred structures or aggregates as they self-assemble. And I'm going to end off with just an example of modeling lipid membranes in terms of how it gets deformed. So lipid membranes, they are fluid membranes. So one of the things is that it can bend, it can kind of curve, and it can also stretch, compress, shear, rotate, so many different things. So in a lot of cases, we have to calculate or model the different free energy penalties that occur because of any movements or any imbalances that occur in the shape and structure of a lipid membrane. So first, a quick recap for DNA specifically. And I wanted to bring some of the key points from DNA because we're going to go through very similar points through this chapter as well. So back when we looked at DNA, there were a few things that we focused on. We had DNA being modeled as sequence and binding site, which we didn't really look at, but specifically we looked at the charged rod, we looked at the elastic rod, and we looked at a random walk model. So we really want to focus on the elastic rod model for this. So first, we know that DNA is made up of a chemical structure of just 4 nucleotides. So basically you have adenine forming 2 hydrogen bonds with thymine, and then cytosine forming 3 hydrogen bonds with guanine. So then you have these AT-CG pairs that create these base pairs along your DNA strand. The special thing about DNA is its electrostatics. DNA is highly negatively charged at approximately negative E over 1.7 angstrom. So DNA is packaged by multivalent cations with 2+ or 3+ charges. So essentially, the key thing that we take away from this is that DNA is very negatively charged. And therefore, because it's highly negatively charged, it can pack into very condensed structures. So those condensed structures are essentially as follows. So this lists out everything. You first start off with your DNA strand, and it gets wrapped into histones. The histones kind of bundle up together into larger aggregates, and then they form eventually a chromosome. So looking at just one of these histone DNA complexes, we focused a lot on just this and how DNA actually preferably or favorably wraps around your histone octamer. So we have this cylinder representing the histone octamer, and then DNA being negatively charged wrapping around the positively charged histone. So electrostatically, it makes sense that they would both want to be together and neutralize their charge. So the one thing that we learned is that the histone tails in yellow are positively charged, and therefore your DNA is going to be stabilized by approximately 200 positive charges on the histone. So what kind of models did we look at for DNA? We first looked at DNA as a random walk model, or basically as a squiggly line. So looking at that, we had an example of DNA looking like a garden hose, or basically just a random coil. And we came up with a few new terms, or terms specific to DNA. We have LP being the persistent length. So that's the length of DNA that we're allowed to call linear. Anything past that, and there is a non-negligible curve to that piece of DNA. So over here, we've labeled this section as a section that looks linear to us. If the persistent length were extended to maybe this, then it would no longer look linear. So the one value or threshold that we looked at was 500 angstrom, which is not something you have to remember, but it's just there to let you know that there are parameters that are commonly used when you're modeling. So from there, we took a look at exactly this persistent length to see, instead of looking at persistent length LP, we just looked at a segment of DNA to see if it's linear or not. So we moved on to the worm-like chain model, or WLC model, and we basically drew two different diagrams. There's the linear segment of DNA, and there's the bent segment of DNA. Now, the reason why I'm bringing this up again is because we modeled this using entropic springs. The key word here is entropic, because the springs represent entropy in terms of energy stored. And because you have a double helix, you end up with two of these entropic springs. So we were able to model the two of these. Basically, when you bend your DNA, you're going to end up with a stretched set of springs at the top and a compressed set of springs at the bottom. So after that, we define persistent length, LP, as the length scale within which the chain remains straight. Anything beyond LP, we're just going to assume that the chain is no longer linear. It starts to coil up. So we noticed through our analysis that the delta L term is very important in determining whether there's bending or no bending. So we have three different cases that we looked at. If delta L is very small and less than the persistent length, then it's pretty much guaranteed that your segment is going to be linear. It means that it's less than what's supposed to be linear, so it has to be linear. Now, if you have delta L being approximately equal to LP, then you're kind of at the threshold. So that means you have a DNA segment that's just bending, but not bending enough that it's going to cause a coil-like structure. When delta L is greater than LP, we end up having a random coil. So we call this coil-like. And one of the things I'm not going to be talking about in this summary or review is basically how to calculate the probability of coil helix transitions and the fractional helicity of DNA. So that's something that was specific to DNA. I don't want to bring it to this lecture. The next thing that we really want to look at is bending energy. So because we looked at a random coil and also the persistent length, it means that as the DNA bends or even wraps around a histone, we need to be able to find the bending energy, or essentially how much free energy there is in the act of bending itself. So we defined bending energy as two different terms. There was a term that represented a microscopic entity, things that were specific to the DNA segment itself, and then there were macroscopic entities for the entire strand of DNA. We also introduced something called the bending modulus kappa B, which is defined by these terms over here, the microscopic entities. So then when we ended up trying to calculate the energy of bending with the worm-like chain model, if you do have a chain that looks like this, you're going to have to essentially draw a circle around each of the main curves and figure out the bending energy for each of those curves and then sum them all up through an integral. So overall, the act of trying to find the bending energy and also the fact that we were able to model the curves using circles along the curve, that's going to be very important for lipid membranes. So after that, we took a look at modeling DNA like a spring. So specifically, we wanted to look at an effective spring constant. So if, without going into too much detail for this, specifically, because we've modeled our DNA as basically two sets of entropic springs, we can consider something called an effective spring constant or an entropic spring constant of DNA, which is given this term. So you can kind of relate this to 1/2 kx squared for a normal mechanical spring, and just say k is equal to all these terms in the middle, and therefore you have the effective spring constant of DNA being equal to whatever variables are left over. Now the last thing we've looked at was modeling DNA as a giant charge. And we won't really look at this too much because I want to focus more on being able to look at lipid membranes in terms of their structural components versus electrostatics. There can be many discussions into the electrostatics of lipid membranes, and I would be really happy to discuss them if anyone is interested in that as a potential modeling project. So just a quick overview of what's happening here. You have DNA being a really highly charged negative molecule in nature. So it has to exist in nature with some counter ions. So there has to be some counter ions that are positive that keep DNA stable. So it has to have that as it's floating around in its regular environment. So then when we introduce the histone octamer, which is positively charged, it's going to attract the DNA. And when the DNA is attracted, we have highly negatively charged DNA with a whole bunch of counter ions attached to it or close to it, and as it wraps around the DNA around the histone, it's going to release the counter ions because the positive charge from the histone will replace the effect of those counter ions. So the one thing about this is that in reality there are approximately 1.75 turns of DNA on the histone, but when we analyzed how many turns of DNA on the histone would neutralize the charge for both, it was 1.4 turns. So because there's more turns in reality than through our modeling, it means that the whole DNA histone complex will have more DNA than we predicted and therefore have a slightly more negative charge than we predicted. So this effect is called overcharging. Next, we took a look at something called DNA twisting, writhing, and linking. So it would just be good to review these terms in case we ever need them. So here you have a very simple DNA strand, which is just a circle. There's no twisting involved and there's no writhing involved. Over here, you have twisting being 3, which means the actual twist of the DNA helix, which you can actually see here, but there's no writhing. Writhing means that the whole loop itself folds in and twists, so you get these nodes. So a writhe of 1 equals to 1 node, and a writhe of 2 equals to 2 nodes, and so on and so forth. But no matter what, the number of twists plus the number of writhes will be equal to the number of links that are possible.